Okay, now we're going to practice how to graph a piecewise function. The first thing we have to notice is that our function f has different parts. For each piece, our function is going to tell us the function it represents and the domain where that function lives. So, for this function f, we will have 4 different functions working as pieces in the graph. Let's start with the first piece. The first thing you will always have to do is identify where the function is living. So the domain for the first piece is from x equals -7 to -2. So the function has to live here. Now, let's start graphing the function. To graph it, because our domain has 2 extremes, we can evaluate. So we're going to evaluate the function in its extremes. So f of 7 means evaluating the green piece in 7, and this is 7. So a coordinate point we're going to plot is -7, 7. Because 7 is included in the domain of this function, in this point we're going to have a field hole. Now, we're going to evaluate in the other extreme. F of -2 is the green part evaluated in -2, -7. This is -3. So our next point to plot is in -2, -3. Notice that because -2 is not included in the domain, at the moment we graph this function, we're going to have a hollow point here. And now our function is a linear polynomial, that is a straight line. So how do I connect these two dots? With a straight line. Now, for our second part, the second piece of my piecewise function is a radical function. And again, my domain has 2 extremes. So the first thing I'm going to do is to evaluate my function in both extremes. So if I evaluate the pink part in -2, I'm going to have that this is 3 times the square root of 0. This is 0. So a plotting point is in -2, 0. Because the -2 is included in the domain for this piece, I'm going to write a field hole like this. Now let's evaluate in the other extreme. If I do this, this would be 3 times the square root of 2 plus 2. That is 3 times 2 equals 6. So another plotting point is in 2, 6. So that's 2, 6. But 2 is not included in the domain for this function, so this is a hollow point. Now, this is a radical function. So we know it can, and it's radical, and it opens upwards. So we know this function is going to open like this. So let's plot some points to identify the correct behavior of this function. First thing we're going to do is to find the vertex of this function. For that, we're going to graph the argument of the function, equate it to 0, and solve for x. So that means that the x coordinate of my vertex is -2. Because we don't have an independent coefficient adding to the radical, that means the y coordinate for the vertex is in -2, 0. Notice that this point is already plotted. So this is a vertex for my radical function. Now I'm going to use the Runrice method to graph. Notice that my leading coefficient is 3. That means that if I run 1, I'm going to rise the square root of 1, 1 times 3, 3. So 1, 2, 3. I'm going to plot my run and rising points. So if I run 1, I'm going to rise square root of 1 times 3. Now I'm going to run another number of which I know easily the square root of 4. So I'm going to rise the square root of 4 times 3, and this is 6. So if I run 1, 2, 3, 4, I'm going to rise 1, 2, 3, 4, 5, 6. Notice that everything is fitting together nicely. Okay, let's go with the blue and orange parts. So for the blue part, notice that my domain is a single point. This is telling me that when x equals 2, the function, that is y, is going to be 1. So when x equals 2, my function is 1. So I have a field point here. Lastly, I have a quadratic value function for when x is bigger or x equals 6 or bigger. So for that, I'm going to first off, I'm going to evaluate my function, my orange function in this point. I'm going to do it here. So f of 6 equals 6 minus 6 squared minus 2. This is minus 2. So when x equals 6, my function is worth 2, so I'm going to plot that point. Now that I have evaluated, I'm going to find the vertex and graph auxiliary points for this graph. So from this graph, I can see that if I graph my argument equated to 0 and solve for x, I'm going to find that I'm just going to move this a little bit. If I grab the argument for my quadratic function equated to 0 and solve for x, I'm going to find the x coordinate of my vertex. And the y coordinate is an independent term. So here's what I have. My vertex coincides with the value I have just evaluated. Now, to finish plotting this graph, I'm going to use the Runrice method. Notice that this is a quadratic function and it opens upwards because my leading coefficient is positive. That means that my function is going to look like this. But careful, the function it's only valid for numbers from 6 to infinity. So let's do something. That means that if I run 1 to my right, I'm going to rise. If I run 1, I'm going to rise the square of that step times the leading coefficient of this expression. The leading coefficient for this expression is 1 because it is not explicit. So 1 times 1 is 1. And if I run 2 times, I'm going to rise the square of that step times my leading coefficient. This is 4. So if I run 2 times, 1, 1, 2, I'm going to rise 1, 2, 3, 4. So my function continues to infinity. And that's how we graph piecewise functions.